Okay, ladies and gentlemen, welcome back to the third part. Now, here, what you're looking at is a long exposure picture of the stars. This is what astronomers would look at or try to study. And from this we've got trigonometry. Now, we have the advantage of, well, rulers and protractors and cameras that can take long-term pictures. Hundreds of years ago, the astronomers had their eyes, and they had whatever equipment they could make. So they couldn't easily make a protractor to measure 360 degrees. 360 tick marks exactly spread out exactly the same distance? No. What they could make were rulers. So they could make a surprisingly accurate ruler. The problem is each ruler would be different. There's no standardized metric system or foot or whatever. So my ruler would be different than your ruler. So what they got in the habit of doing, measuring ratios. So a star here, you could measure the adjacent and the opposite. Now, and get a triangle. By the way, this would be a right angle triangle. Now, what they would do here is do these measurements all night long. So, this star would start here in the first quadrant and go over into the second quadrant if they watched long enough. And if they were north enough and watching the right star, they could see it come around in the third quadrant and then eventually into the fourth. And this is where our quadrants came from. So that's where the stars started. First, second, third, fourth, and that's the direction of rotation. Now, as I said, these early astronomers made their own rulers. Life. Now, for them, there were a couple of triangles that were good, easy for them. So if we look at the origin, the first one was an isosceles triangle. 60 degrees, 60 degrees, like that. Now, we measured on both sides. You had the x-axis. You came up with a nice isosceles triangle. Now, we cheat. Because here, cut it in half. This is 30 degrees. And there is a 30, 60, 90 right angle triangle. Why are we so interested in that? Well, let me show you. Say each side is 2. Then what's this length here? Half of 2 is 1. This length, if you do Pythagorean's theorem, square root of 3. Now, don't have to copy this out. This is something you should be able to figure out. 1, 2, square root 3. Now, this is getting a little messy, so I'm going to redraw it here. Now, the advantage to this is that it makes our calculations very simple. Let me show you. What's sine of 30 degrees? Well, the sine is the opposite over the hypotenuse. What's the cos of 30 degrees? Well, by definition, cos is adjacent. And tan of 30 degrees is the opposite of the adjacent. Now, if you check these with your calculator in degree mode, sine of 30 degrees is a half. Good. Cos of 30 degrees is 0.866. No, it's not. That is a decimal approximation your calculator is giving you. You have to realize that this is root 3 over 2. And tan of 30, 1 over root 3, 0.57 something. No. It's 1 over root 3. Now this is important because for two reasons. One, you have to know this triangle, and two, you have to realize these are coordinates. Okay? That's root 3 comma 1. Now, so far so good? Good. Now, if we go over here and draw another 30-degree triangle, this is 1, this is 2. In the second quadrant, x is negative, so this is minus root 3. Now, normally we don't talk about 30 degrees there, we talk here 150 degrees. So sine of 150 degrees, cos of 150 degrees, and tan of 150 degrees. So sine is opposite over hypotenuse, a half. Cos is adjacent, minus root 3 over 2. And tan is opposite over adjacent, 1 over minus root 3. Now we would probably write that as minus 1 over root 3. Be careful, that minus sign could get smeared into the division and disappear, and we don't like that. Now, so far so good? So going on, we get down here. Here's another 30 degree. Now, this is 180 plus 30 sine, so that's 210. And this would be minus 1, 2, and minus root 3. So sine of 210 is minus 1 over 2. The cos of 210 is minus root 3 over 2. And tan is tan of 210 is minus 1 over minus root 3, or 1 over root 3. So far so good? Should see a pattern forming. So I'm going to go over here. Minus 1 down. So that's 2, not root 3. Now you guys, if this is 30 degrees, this has got to be 330. So sine of 330 degrees, cos of 330 degrees, and tan of 330 degrees. So you guys do those. Come up with an answer. Sorry, pause this recording, come up with an answer, come back and check. All right, welcome back. So sine is the opposite over the hypotenuse. Cos is the adjacent of the hypotenuse, and tan is opposite over adjacent. It's minus 1/2 root 3 over 2, minus 1 over root 3. Now, you don't absolutely have to memorize this, but it would make life so much easier if you did. Now, I'll give you a minute to look at that, because I'm going to go on and look at a 60-degree triangle. Woohoo! Right. So moving on, what does a 60-degree triangle look like? Well, it's going to be 2, 1, root 3. So sine is 60 degrees, cos is 60 degrees, and tan is 60 degrees. Sine is opposite over hypotenuse. Cos is adjacent over hypotenuse, and tan is opposite over adjacent, which simplifies to just root 3. Now, I want you guys to pause the recording, and I want you to figure out what the other angles are going to be. That is this triangle here, this triangle down here, and this triangle down here. So go for it, pause the recording, come back, and we'll check our answers. All right, welcome back. So 2 root 3 minus 1. So if this is 60 degrees here, this has got to be 120. So it's sine of 120 degrees, cos of 120 degrees, and tan of 120 degrees. So sine is opposite for hypotenuse. Cos is adjacent over hypotenuse. Notice minus 1/2. And tan is opposite over adjacent. So it'd be root 3 over minus 1 or minus root 3. Moving on. This angle down here is 180 degrees plus 60 or 240 degrees. Tan, I start sine for some strange reason. Sine of 240 degrees. Cos of 240 degrees. And tan of 240 degrees. Now, this is minus 1, this is minus root 3, and this is 2. So sine is opposite over hypotenuse, minus root 3 over 2. Cos is adjacent over hypotenuse, and tan is opposite over adjacent. Good. Now the last 60-degree triangle, or this whole thing, would be 300. So sine of 300 degrees, cos of 300 degrees, and tan of 300 degrees. Sine is 2, 1 minus root 3. Know the sides of my triangle. In the fourth quadrant, x is 1, positive, the y is negative, and my radius is always positive. So opposite over hypotenuse, minus root 3 over 2. Cos is adjacent over hypotenuse, and tan is opposite for adjacent. So that you should see, that you should be able to check with your calculator, but more importantly, you see patterns. Root 3 over 2, not 0.866, 1/2, and root 3. So they keep repeating. All right. Now, that's 2 of the 3 triangles you got to know. The other triangle, going back to this, when they're looking at the stars, the easiest one is a 45, 45, 90. Now, if you think about it, that's 1. Actually, what they did, I'm sorry. The easy way you guys would remember this, take a box that's 1 by 1. What's the diagonal? Well, 1 squared plus 1 squared is 2. So the hypotenuse is square root of 2. Or the radius, I should say. And this is 45 degrees. So sine of 45 degrees, cos of 45 degrees, and tan of 45 degrees. Now, sine is opposite over hypotenuse. Cos is adjacent over hypotenuse. And tan is opposite over adjacent. So far, so good? Now, one little thing to note here. For reasons best left in antiquity, they don't like a square root sign in the denominator. So what we'll often do, not always, but often, rationalize the denominator and write it like that, root 2 over 2. 0.707 something something something. Multiply top and bottom by root of 2. 1 times root of 2 is root of 2. Root of 2 times root of 2 is square root of 4. The square root of 4 is 2. So, depending on my mood, I will write it as either 1 over square root 2 or root 2 over 2. Not deliberately have to confuse you, it just sort of happens that way. Now if we go into this second quadrant, this is 45 degrees. What's this angle here? 180 minus 45 is 135. Okay. So, excuse me. So sine of 135, cos of 135, tan of 135. Sine is opposite over hypotenuse, 1 over root 2, or root 2 over 2. Cos of 135 is adjacent, and tan is opposite over adjacent, or minus 1. Now, I want you guys to pause the recording, and I want you to go and do the other angles. Come back and check your answers with ours, or mine, I should say. And then we'll finish up. Okay, so pause the recording now, please. All right, so if this is 45 degrees, that's 180 plus 45, which is 225, so it's sine of 225 degrees, cos of 225 degrees, and tan of 225 degrees. Root 2, oh, this is minus 1, so sine is opposite over hypotenuse, minus 1 over root 2, or minus root 2 over 2. Cos is minus 1 over root 2, or minus root 2 over 2. And tan is going to be minus 1 over minus 1, which is 1. Over here with this 45 degrees, this is going to be 315 degrees. So sine is opposite, oh, getting ahead of myself, root 2, 1, and this is minus 1. So it's minus 1 over root 2, or minus root of 2 over 2. Cos is adjacent, my x value. And tan is opposite over adjacent, which is 1. All right, so far so good? Now you've only had to do 3 triangles, or technically 2 triangles here. The ancient astronomers did every angle to a 1/10 of a degree. Yes, a 1/10 of a degree. That is 3,600 angles exactly. No decimal approximations. Now, just want to point out here, these are the angles you have to remember. Okay? Now, when can you do decimal approximations? Well, you can do a decimal approximation when it's not 30, 60, 90, or 45 degree angle. So if I go cos of 42 degrees, you're going to go cos 42 and get 0.743144, blah, 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 blah. Rounded off to 4 decimal places unless I say otherwise. Now, so far so good? Oh, just as an aside, there's a couple questions for homework. If I say cos of theta is 0.1841, what's theta? Well, you do inverse cos. You can use decimal approximations when it's not 30, 60, 90, or 45 degree angles. So I'd round this off to 79.4 degrees. Okay, so that's one of the questions on your homework. Now, as I said, this is good stuff to know. If you can memorize these triangles, I'd appreciate it. Or then you can come up with these trig ratios to make life a lot easier for you. All right. Now, good luck. Give the homework a try, and I'll see you tomorrow.